Hello and welcome to the first lesson of Cambridge International Education IGCSE Physics, Unit P1, which is motion, force, and energy. And the first lesson is on SI prefixes, length, and time, or units and measurements that I've summarized as here. So our learning objective for today, I describe how to use SI units and prefixes, successfully measure length, time, and volume with different apparatus, or show you how to do it. Obviously, you won't be able to do it yourself at home as easily, and calculate the mean from a set of data. So the first learning objective for today is describing how to use SI units and prefixes. So the SI system is now used in pretty much all countries. It is a decimal system in which units are divided or multiplied by 10 to give small or larger units. And there are something called base units, and these are them. And all other units are derived from these five SI base units. There's actually one more, which is the mole, which they use more in chemistry, but I've not included on here. So technically, I should say 6 units. Okay, now the quantity, unit, and symbol are here. Quick task, you can fill these in yourself. So the first quantity, the unit is meter, the quantity is length, the symbol is m. Quantity mass, the unit is kilogram, symbol kg. Ampere, usually abbreviated to amps or amp, is current, and we use letter A for amps. Now this is S, so that is time in seconds. And finally, Kelvin, you might not have heard of this one before. That is temperature. And we use letter K. And like I say, there's one more, there's the mole. We use the symbol MOL, and that is for more of a chemistry one. Okay, so like I said, these are the base quantities plus the mole. And you can also derive them. So, for example, speed is distance divided by time. Now, there's many different units we can use for distance and time, but if we use the SI units, we're going to use meters, and we're going to use seconds for time. So meters divided by seconds, so we get meters per second, or m/s. Sometimes you might see it as ms to the -1. So the slash means per, or if you have s to the -1, that also to the -1 also means per. So it's meters per second there. Now, prefixes such as milli and kilo are placed before units. They are especially useful when the quantity is very small or very large. So I will put some of these that we use quite commonly on here. You probably only really need to know up to 10 to the 9 and up as low as 10 to the -9. Probably worth taking a screenshot of this and keeping it, because you do need to know all of these. So we're starting big. Giga is 10 to the 9. Now, they generally go down in 10 to the 3 powers. So you've got mega, 10 to the 6, also could be called a million. Kilo or killer is 1,000 or 10 to the 3. Centi, there's the one that doesn't go to the power 3. And the only time you really normally use centi is in distance, is the main one, centimeters. Sometimes we use centimeters, so 10 to the -2 or 0.01. Milli is 10 to the -3, so for example, millimeters. And if I wanted to go from, say, I'm given a certain number of millimeters, I would divide by 1,000 to get in meters. So for example, if somebody said 500 millimeters, I would divide that by 1,000, and I get 0.5 meters. Micro is a small number. We use this letter mu symbol here, 10 to the -6. And nano is 10 to the -9. N for nano, N for -9. Okay. So, quick task for you is to convert each of these into what I've put on the right. Okay, so we've got 134.6 seconds. To go from seconds to milliseconds, you times by 1,000. So this number here. We've got meters going to kilometers. So there's 1,000 meters in a kilometer. So it'll go from meters to kilometers. We divide by 1,000. Or you could say divide by 10 to the 3. 12.873. To go from kilograms to grams, there's 1,000 kilograms, say 1,000 grams in a kilogram. So you would take this number and times it by 1,000, 0.79. We've got 96.2 nanoseconds, so that's 96.2 times 10 to the minus 9, which gives me 9.62 by 10 to the minus 8. And then 2.56 gigagrams to kilograms. Now, this one's a little bit more complicated. Okay, so if we look back at what we said earlier, giga means times 10 to the 9. Kilo is 10 to the 3. So the difference, 10 to the 9 divided by 10 to the 3, gives us 10 to the 6. So you do 2.56 times 10 to the 6. And now it's the other way around. We're going from millimeters to kilometers. So 75 millimeters. And then we're going to kilometers. So we divide by 10 to the, so we've got 10 to the minus 3. Then we're dividing by 10 to the positive 3. So that gives us 10 to the minus 6. So it's 75 by 10 to the minus 6, or 7.5 by 10 to the minus 5. Okay. Next learning object is about measuring length, time, volume of different apparatus. So a key term which you don't actually really need to know how directly, however we do use it quite a lot. So you'll have to sort of describe it without knowing the term, so I might as well put a term in there, is resolution. So it's the smallest change in quantity an instrument can measure. So this ruler here only measures to the nearest centimetre, so it's got a resolution of 1 centimetre. This ruler here can measure the nearest millimetre, so it's got a resolution of 1 millimetre. So depending on what you're measuring, you want an appropriate resolution. So for example, I don't need this 1 millimetre if I'm measuring the distance there from one city to the next. We don't really need that to the nearest millimetre. Probably don't even need the nearest centimetre. We're probably going to go to the nearest kilometre, which is an appropriate resolution for something like that. So you need the equipment which is big enough to measure the quantity, but with the best possible resolution. So what would you use to measure each of these? The height of a phone. Well, you just look in the corner there, see my picture. You can see there's my phone. Without getting my ruler out, I think that's about 15 centimeters high. See how close I am. Pretty close, 15 and a half roughly. So you're going to use a ruler. Distance from here to, say, I put the admin blocks, that's from my school, so maybe a better question would be distance from your house to the next door neighbor's house. That'd be a better one. So I would use something like a tape measure or a trundle wheel. So that's a wheel which you put on the ground and you move with it. Every meter here a click, so you have to count the number of clicks. So you'd use a tape measure or trundle wheel. Length for house key. Average house key is probably about 5 centimeters, so I think a ruler is probably okay for that. Now the thickness of a house key, a little bit harder. You're probably looking at a couple of millimeters. So if you think, let's say it's 2 millimeters, the thickness of a house key, and you're using a ruler which only measures to the nearest millimeter, you've got about 50% error. So you want something with a much better resolution than that. So to measure the thickness of a house key, I'm probably going to use something like a micrometer, or micrometer screw gauge to use its full name. And it looks something like this. Now, you don't necessarily have to be able to use one of them. However, you do need to know that it's used for measuring very, very small thicknesses, a micrometer. Okay, you can use it for this one here. It looks like it's measuring to the nearest 0.01 millimeter. So very, very high resolution there. Okay, so how much water is in this measuring cylinder? Now, it's a little bit hard to judge exactly because of the angle I've taken this picture. You can't really see too well how much is in there. So when you measure something, you should measure from what's called the bottom of what's known as the meniscus. So this is the meniscus here. You see it's got a slight curve on it. Okay, and the bottom of the meniscus, so my eyes should be level with that. And it looks like I'm on about 26 centimeters cubed, or milliliters. 1 centimeter cubed is the same as 1 milliliter. So a measuring volume always measured from the bottom of the meniscus. Okay, that's something you do need to know. And it quite commonly comes up on paper 5 and paper 6. So the mean and average can be calculated by adding all the values up and dividing by how many values you have. So again, it's another key term you need, and you've probably done this loads and loads and loads of times, including probably even at primary school, perhaps. So 2 dice were thrown 10 times, and their scores were added together and recorded. Find the mean for this data. So add them all up. There's 10 results. Divide by 10. I get 7. Okay. One thing to look out for, now it's dice, so it's not really easy to compare, but if you're doing an experiment and you had a set of results, if one of them was, say, 50 and the rest were these, there's probably quite a bit of error there. So you've probably made a bit of a mistake, and you should probably ignore that one result, which is very, very different to the rest. And the last little bit to cover today is the period of the pendulum is the time taken for it to swing from one end to another, then return to its original point. So, for example, start now, start the stopwatch, finish it here. That is the time. So it's not from there to there. It's from here to here, then back to the beginning. However, you wouldn't normally just do one swing. Now, I'll give you a second to think about that, and I'll explain why in a moment. Okay, the reason for it is, for this pendulum here, without getting my stopwatch out, it looks like the time taken for one oscillation is approximately 1 second. Human reaction time is about 1/4 of a second to 1/2 a second. So if we look at the top end of that, say 1/2 a second, again, there's quite a lot of errors, about 50% error. Whereas if I do, say, 10 oscillations, so let's start here, back, 1, 2, 3, etc. Then after I do 10 oscillations, let's say it takes 12 seconds for argument's sake. 12 seconds, and then divide it by 10, and I get 1.2 seconds. So my error has now gone from about 50% we talked about earlier. I do 10 oscillations, it's gone down to about 5%, which is a lot more acceptable. Okay, so like I say, this here, these kind of pendulum questions commonly come up on paper 5 and paper 6, either the practical exam or the alternative to the practical exam. So what I've put here is an example of a paper 5, sorry, paper 6, alternative to practical exam paper question. You might want to, if you've got it printed, it's the perfect one to take a screenshot and then print it out and try it yourself. Or alternatively, you can try doing it on the screen, depending on what device you've got. And I'll let you pause it, work through it, and I'll go through it in a few seconds. Okay, so the student investigates the period of a pendulum. Explain how to measure the center of the pendulum bob as accurately as possible. So you measure from the clamp to the center of the pendulum bob. Place a ruler next to the pendulum and ensure it's touching the bob. So there are other ways you can do it. You can measure the string, and then you can also separately measure the bob, taking into account half its thickness, and add it to the length of the string that you are using. Okay, so the student adjusts the length of the pendulum until the distance L measured from the bottom of the clamp supporting the pendulum to the center of the bob is 50 centimeters. It displaces the bob slightly and releases it so that the swing is shown basically in this table. He measures and records the time for 20 complete oscillations, calculate and record in table 1.1 the period of the pendulum, and also record t squared. So 20 oscillations, so you do 28.2 divided by 20, which gives me 1.41, and t squared is just 1.41 squared, which gives you 1.99. The mark scheme says here for this one, you need to be at 2 decimal places only and correctly rounded. So if you've put 2, that's wrong. Or if you've put 1.993 or whatever it is in the calculator, you also don't get. So this needs to be 2 decimal places, the same as basically everything else in this row here. Then plot a graph of t squared against L. Start the t squared axis at a convenient value close to the minimum value of t squared. So I'm going to do L first. So I'm going to start at 40, 50, 60, 70, 80, 90. And then our lowest value of t squared is 1.99. So I have to go below 2. So I'll start at 1.5 and I'm going to go up in half intervals. Okay, I then plot all the points. And a good line of best fit shouldn't just be a dot to dot. You won't get marks for that. It should go through several of the points, or if not, so a better way to describe it would be it should have the same number of points to its left and to its right, which this line approximately does. You can see goes through this point and this point, and it kind of goes through this one. This one's a little bit to its right, this one's a bit to its left. So the mark scheme specifically says axis correctly labeled with quantity in units. So you have to have L/centimeters and you have to have t squared / seconds squared. Suitable scales, similar to the ones I've done. All plots correct to the nearest half square, and a good judgment thin continuous line. Now, I've probably done my line a little bit too thick, but I did that so it's easy for you to see. It should be fairly thin, your line, not too thick. And so the next part of the question was determine the gradient of the graph, show clearly how you obtain the necessary information. So the easiest way to do it is draw a big triangle. You should have put this in maths. So I always just do it to the furthest point on the right to the furthest bit on the left. Now, I'm not actually using the points, I'm just doing where I've plotted on the graph. Gradient is the change in y divided by the change in x. So 3.65 minus 1.55. Change in x is 90 to 40, so 90 to 40 is 50. You get a gradient of 0.042. So the mark scheme says triangle method clear on the map, so you have, on the graph, sorry, so you have to have done shown a triangle. Triangle at least half the length of the line between the extreme plots used. So I've used the entire graph. You don't have to use it, but it should be at least half it. And then your final gradient should be in the range of 0.038 to 0.044. Mine's 0.042, so it is within that range. And then finally, explain briefly why timing 20 oscillations gives a more accurate result for the period than timing 1 oscillation. Reaction time is large compared to the time taken for 1 oscillation. Okay, so it reduces the error. Okay, let's have a look at some paper 2 multiple choice questions. The diagram shows a pendulum that oscillates between P and Q. Which method is used to find the average period of oscillation for the pendulum? Measure time taken for a swing at P to Q. That is only actually half an oscillation. It's going to have high amount of error. Measure the time it takes to swing from P to Q back to P 10 times and divide that by 10. That sounds like a good method, but we'll just check the rest just in case. Measure the time it takes to swing from P to Q to P 10 times and multiply by 10. Well, actually, you're going to get 10 times the time period. I'm going to times by 10 again, so you're going to get 100 times the time period there. That won't work. Measure the time it takes to swing from Q to P. Again, that's half an oscillation. So B was indeed correct. The next question, which measurement instrument is used to measure the diameter of a thin metal wire? So it's probably going to be maybe less than a millimeter, so you're going to need something to measure that to that level. The first 3 things certainly won't. A micrometer, screw gauge probably will, though. A student is taking some measurements. Which measurement is taken directly using a micrometer screw gauge? You can't measure millimeters squared, millimeters cubed, or this looks like something you can't directly measure. You can only measure length, or say distance or thickness. So that would be millimeters. And the last one, the student investigates a pendulum. He measures the time For the pendulum to complete 20 oscillations, it repeats the experiment 3 more times. The readings are shown. What is the average period of the pendulum? So I'm just going to add up the time for 20 oscillations. So I'm going to do 17.6 plus 19.8 plus 17.6 plus 18.6. That gives me 73.6. And divided by 4 gives me 18.4. However, that is it for the average for 20 oscillations. So I need divided by 20. That gives me 0.92, which so the answer is therefore B. Okay, so that's it for today's lesson. Next lesson will be on density of solids, and I will be uploading that fairly soon. And we'll post a link down in the description. Thank you very much, everyone. I will see you in the next video.